Welcome to Unit 2 of COMP526. We'll talk about fundamental data structures, things that some of you will know, others will not have seen. We'll go at a pace that's not right for anyone. It's too fast for those who haven't seen it, too slow for those who've already seen it. But it's the best I can do in a single lecture. I try to give additional material online, and I try to give some hints and connections that people who have seen it before might not have heard, because they're a little additional to the standard content. That's my way of trying to strike this balance. I hope it works somewhat for all of you. I do love this unit because it's beautiful topics. Even though they're quite basic, there's lots of beautiful ideas in it. And I hope at least you can take some appreciation and joy out of those, even if you have seen them before. The outcomes for me, the biggest one maybe is the distinction between an abstract data type and an implementation of a data structure, or an implementation is a data structure in this sense. We'll talk about that at length if you haven't seen it. I think this is just conceptually very useful in many different applications. It helps you become better programmers as well, I think. So we want to be able to define concrete examples of abstract data types, ones that occur often. And these are the ones. We want to understand very basic implementations, data structures that implement some of these abstract data types, and two slightly more sophisticated ones, but still undergraduate level. And those are binary heaps and binary search trees. Okay. There's quite a few of sections. These sections basically reflect the videos that I made last time. So each of the sections should be between 10 and 30 minutes of lecture. So you see this fills 2 full days, and probably I won't be able to squeeze it into 2 days because we started a bit late. We'll talk about very fundamental data structures and how to implement them, and then about priority queues and how to implement them, then about symbol tables and how to implement them. And split up so that it's in digestible chunks. Let's start with stacks and queues. And before we continue with that, I'd like to have a quick look at Slido to see how much you have seen of this. Okay, so a few people have not seen any of the data structures. Most people have seen arrays and linked lists. But not so many binary heaps, okay? But many more people, binary search trees. That's interesting. Good to know. Fibonacci heaps is a much more sophisticated version of priority queue, just a few skip lists, hash tables. We won't talk about hash tables at length, even though I would like to, but had to make a cut at some point. Okay, thanks a lot. That means I should probably, on the binary heaps, at least give you a fair chance to understand them, if so many haven't seen them. But before we get to that, let's start with the more basic stuff. And the first thing is this distinction I already mentioned in the outline. What is an abstract? Sorry guys, I didn't switch the screen. What is an abstract data type? And what is a data structure? An abstract data type is basically an interface that gives access to certain data in a certain way. And we do this by supplying certain operations that we support. We'll see examples soon, which makes this probably a bit more tangible. The abstract data type only tells you what should happen. It doesn't tell you how to store the data. It doesn't even talk about any kind of storage or representation. It doesn't tell you how to implement the operations, how these are done. It just tells you what you're supposed to do and what the operations allow you to do. In programming languages, there's some support for doing abstract data types, for realizing that in languages, but none of them is complete in exactly reflecting what an abstract data type is. For those of you who know Java, there's the interface construct, and Python has something like this as well. Can I have a quick hands who has seen abstract base classes in Python? That's like a handful of people. It's it's a topic that might not be covered as often in Python because it's considered a bit more advanced. But if you want object orientation in Python, you hardly get around it, I'd say. If you haven't seen it, maybe I can find some nice tutorials. It's not really relevant for us, but it helps you link things if you have seen it. So in Python, there's a way to represent interfaces similar to that, where you can say any object that I want to consider of this type should have these methods, should have functions of this name. I would say in both cases, we want to include the comments that explain what the functions do as part of the interface or part of the abstract base class, because this is what an abstract data type also tells you. It has operations and an explanation what they do. And let's contrast that with data structures, which exactly tell you how to represent data, not just what to do. They tell you exactly how operations are implemented, what are the algorithms for doing that. And you can, for a data structure, precisely analyze how much space does it need and how long do the operations take. Again, in the worst case, in the average case, all these things we discussed last time on a word RAM or by counting fundamental dominant operations. This is what you've seen. And in Java and Python, these are basically classes. So a class is a template for creating objects. An object is a specific instance of a data structure, and the class is the implementation, is the data structure itself. That's how it maps to programming constructs. Why do we want to separate these two things in the first place? I think there's a practical reason. In programming, it's just very convenient to decouple things so that you can change one part of the program, maybe improve it by replacing with a more sophisticated and more efficient implementation, without having to change the rest of the code. People call this a drop-in replacement. You can just take a piece of code, change it to something else, and the rest will remain working without any further changes. That makes code reusable and allows to build libraries, in a sense, in the first place. I also think conceptually it helps because better abstractions give you a name, so a complicated concept can become a single variable, a single name for you in your brain. That helps you build bigger systems. We'll come back to the last point. A little warning at this point, though. Sometimes, as in this picture, things can go a little awkward. If you have interfaces and you limit yourself to an interface, it might look like this is a tab somewhere that you can only access by turning there. But actually, there's a long hose attached to it. And if you need it to get water somewhere else, it might be better to just detach that hose or at this point, whatever, and pull that over. So sometimes it's useful to break open the encapsulation, the abstraction of a data type and look at what is inside. So don't slavishly follow a certain interface if it looks like you're building something like on the picture that stops you from implementing optimizations you otherwise would have had. But it looks nicer to use this. That's why people like abstract data types as well. Okay, we've discussed this. Sorry, no, we didn't. I thought that was the other question. You didn't see anything, right? Did you? Let's try this quickly. For those who have seen these, which are examples of abstract data types? Now, of course, everyone's at home is at the advantage of just scrolling back at the video. Okay, I think we're expecting some 10 more people, something like that. Okay, I'm locking the question. 5, 4, 3, 2, 1. Oh, someone just last minute submitted their result. Okay, so you can see on your phone how you did, and I'll switch back. I will discuss all of these later. So just very briefly, stack and deck. So deck is a queue and a stack in one thing. These are abstract data types, queue as well, and priority queue and dictionary or simple table. And the others are either just an abbreviation or they are data structures. Let's make this more concrete and look at one specific simple abstract data type, and that's the stack. And here is the list of operations that a stack can support. It can give you the topmost elements. So you think of this stack of books, and you're not allowed to play this balancing game. You're not allowed to pull out a book from below. You can only access the topmost book. You can add a new book on top, though. That's fine. And you can remove the topmost. So the difference between top is top just lets you look at the topmost, but leaves the stack unchanged. And pop takes the topmost off and returns it to you. Okay? And, well, a few other less exciting methods. You can check if the stack is empty. That's often convenient. And you can start with an empty stack. Do the operations make sense? So notice again, there's this stack of books, which has nothing to do with the computer. But this stack of books is somehow an implementation of this idea of a stack. And that's how I would like you to think about abstract data types. They only tell you how things happen. They don't show how you actually organize data. But we'll, of course, come back to that as well. All right, let's do this. A quick question on whether you follow this. It should be an easy one. Okay, I'll give you a few more seconds, but the results look fairly clear. Three, two, one. Ah, this tension. Okay, so this seems to be quite clear. Where are we? So that's the right answer because basically we have the stack shown like this: 5, 4, 3, 2, 1. I'd like to have this black rather. Then we pop the first two off, so these are gone. I could actually just erase them. Then we push another 1 on top, and if you read this top down again, then we get this answer. Okay? So you understood how this stack works. That's great. Then let's rush on. Something that many of you will also have seen is how you can implement a stack. There's different ways. One is to use a linked list. And many of you have seen this, so let me do this very briefly. The idea is you maintain a pointer top. That's a global variable, which points to the topmost element in the stack. And then here's one element, say our 1 from before, and another pointer which points to the next element further down in the stack. So that was 3, and then this points down here. And we had 2 more. We had 4, 5, and this pointed to this one, this pointed to this one, and this one pointed nowhere. It was null, so that's the end of the stack. That's how, now you can figure out how we can implement all the operations, but I think most of you have seen this before. So what I draw by these boxes and arrows is an abstraction of how you would implement this in a program, in a computer. The pointers, these arrows are addresses in memory. You use objects. Maybe there's a class in Python that has these two fields, one for the element and one for a pointer to another box. And then these are represented as just memory addresses where this next object begins. I assume this is something you've seen before, or at least you've done something like this in the Python introduction or in your undergrads. Let's have a quick look at the analysis, though. I don't know, this is maybe something that not all previous courses have emphasized. We need, for every element on the stack, we need one of these boxes. So it's linear space. We can express this in our fancy new notation. It's theta of n space. And we can measure the space in computer words. Again, that's the word RAM model. If we have n elements currently on the stack, and the operations all take constant time because they all mean follow a pointer from top and then do something with this topmost element, either return it or remove it and return it, or create a new object on top, point it to the previous topmost, and rewire top to point to this new one. So these are all things that take a constant amount of time. It doesn't depend on how high the stack is. Okay? So this is actually brilliant because this is the best you could hope for. We definitely need linear space to store all the elements, and we can't get better than constant time for the operations. So in terms of these theta classes, we cannot hope for any better implementation of a stack. This, if you look a little closer though, there's a little disadvantage of this. We need to store n pointers for this linked list-based stack. And that's a little wasteful. We only really need to store the elements in an ideal world and not as many pointers on top. So maybe we can get rid of those. And we can by using an array instead of a linked list. And let me draw the array like we draw stacks. So start with 0, 1, 2, and then count upwards. So we can also represent our stack in here by storing the elements like so. And we have again a top is again a variable for the entire stack, and that just stores the index of the topmost. No one can read this, but it's supposed to be a 3. So we just store the index of the topmost element currently in the stack. So we have this array S, and we maintain the topmost position. Now, there is a catch with this, and that is if we filled the array entirely, so if top is the size of the array, then what should we do upon a push? If we get another push and the stack is full, we don't have space in the array, so we're throwing our hands up and start crying. So what this is at the moment is a fixed capacity stack. We have, at creation time, we have to tell what's the maximal number of elements we're ever going to put into this stack, and we can't push more elements than that. Then we need theta of C space. Again, if C is too small, you're screwed. If C is too large, you waste the space. What's good is all operations are again constant times, and they tend to be faster than in the link-based representation, a smaller constant. But it looks like we started with this idea, let's try to save space by not have pointers. And now we still have this problem that we need to know the final size, and looks like we're we're not improving on space so much. So there's a slight modification of this, which rectifies at least the problem that we need to know this capacity. But it turns out to some degree you can't completely avoid having extra space. You need a little bit of extra space if you want to have the ability to grow beyond size. And there's some interesting, quite complicated theoretical data structures that try to push this to the limit. But we won't cover this.